Hi there. In this video, we'll look at topic 4.5, linearization. For this video, I chose an example from page 242. This is problem 2 from the homework set. And we have two tasks. Number one, we need to find the linearization of, the linearization, which is called L of x, of the function f of x, which is given here, at the particular point of interest, which happens to be an input of -4. So we'll make some meaning out of that and then do it. Part B, once we determine the linearization, we want to determine its accuracy in terms of approximating the function. So how good is that approximation? All right, and before we dive into this particular problem, let me just make some general comments about the theory of lines. It's probably useful to know these outcomes. If you're going to do a bunch of problems with linearization, you might as well know some things about the structure of that. All right, so let's just take a trip backwards in time to Algebra 1 for 2 minutes. And let's talk about the equation of a line that has a particular point and a particular slope. So this line has slope 1/2, and it goes through the point 2, 5. What is an equation for this line? Well, let's choose a point somewhere out here in the distance, and we'll call it x, y. So this coordinate is x, this coordinate is y. And when we look at the vertical distance between them, the distance is the difference between these two numbers. And the horizontal distance here is the difference between these two numbers. Okay? So in other words, when we look at this triangle right here, we know its width and its height. Okay? And these two triangles are similar, the big one and small one. So we can use what we know about similar triangles to say that the ratio of this vertical side to the horizontal side should be equal to the ratio of this vertical side to this horizontal side. Okay? So that's just kind of the background on the slope formula. And the part that I want to emphasize in this video is if you want to solve for y, you have to do two things. Number one, multiply both sides by the quantity x minus 2, and that will cancel out. And we get y minus 5 equals 2 times x minus 2. And we just add 5 to both sides to get an equation for the line that is solved for y. Okay? So this is something that we practiced in calculus all the way back to chapter 2. But let's upgrade it. And again, purpose for this video is to understand how to do that with symbols. And this will allow us to take a little bit of a shortcut in our work with linearization. So here goes. What if I have some curve that goes through the point A, f of A, with slope f prime of A? Okay, so how does that look? Well, here's A, f of A, and we'll call this, again, general point xy. Okay, and let's even use the function notation, again here, to be consistent. X, fx. Okay, so what is the equation for this line, knowing that the slope is f prime of A? Okay, well, let's apply the slope formula. So we have the difference in the y values, fx minus fa, divided by the difference in the x values, which is the difference between x and a, is equal to the slope, which we're told has the value f prime of a, equals the slope. Okay, and let's perform those same algebraic maneuvers as we did on the previous screen. Multiply both sides by x minus a, and we get f prime of a times x minus a, and then we can add fa to both sides, and we get fx is equal to fa plus this other stuff. Okay, and typically we're going to now call this Lx, as in the linearization, because this is the equation of the line. So if fx is the curve, then Lx will be the line that's tangent to the curve. Okay, and so again, I just went through that just so that we can save a little bit of time. If we're going to do a whole set of homework problems, we might as well know this result and just apply it. All right? So as I work through the problem, I'm just simply going to go right to this result, take the output, take x minus the input, and multiply by the slope, and we'll need to, of course, get the derivative to know what the slope is. All right, so that's going to happen from now on, and let's get to it. Okay, so looking back at task part A, find the linearization. What does that mean? Well, that actually means that we want an equation for the line that is tangent to the curve at that point. That's what linearization means. And so as we saw in the previous examples, we'll need a point on the curve. So what's the output that goes with the given input? We'll need the slope of the curve. So what is the value of the derivative function at that number? And then we'll just write down an equation for the tangent line. So let's get started. All right. Let's call this 1. So step 2, let's just go ahead and plug in the particular input that was given to us, which is -4. And let's see what comes out. So -4 squared is 16, add 9, you get 25. And the square root is going to be 5. Okay, so that tells us that the point -4, 5 is on the curve. Let's pop over to Desmos. And I have typed in the function right here. And let's just go ahead and get the input and the output to verify and visualize. Okay, so our work showed the output was 5, and the technology confirms that that is correct. Okay, so now we have a point on the curve. Let's continue by finding the slope of the curve at that point. And for that, we're going to need a derivative. Derivatives love power, so I'm just going to write every chance I get. I'll write problems as powers. Now I'll use the power rule to take the derivative. So f prime of x would be, let's bring this power down, so you get 1/2 of the expression to the power of -1/2. And the chain rule tells us to multiply by the derivative of the inside, which is 2x plus 0, or just 2x. Okay, and we want to now evaluate that derivative formula when x is -4. So let's go ahead and plug in -4 into our formula and see what comes out. Here goes. Plugging in -4. Okay. Once again, we get 16 and 9 is 25. So this is 1 over the square root of 25. That's what that exponent tells us to do, which is just 1 over 5. Can I save time by erasing? That's a 1/5. Bring down the factor of 1/2. Bring down -8. And we can multiply these things together. So 1/2 of -8 is -4. And we want a 1/5 of that. Okay. So all this work is just showing that f prime at this input is -4/5. Okay, that was the outcome of all this work. Okay, now let's see if we can answer the question in terms of finding a formula for the linearization of this function at that particular point. All right, so tying it all together, and I'm just now using the result that we established in the previous slide. Lx is the output, which is 5, plus the slope, -4/5, times x minus the input, minus -4 is plus 4. And so this right here is the linearization of our function at that point. Let me now pop over and type this equation into Desmos. So 5 plus -4/5. We'll call this g of x. 5 plus -4/5 times x plus 4. Okay? And notice that that is hitting the target point, and it does appear to be tangent to the given curve. So that's awesome. All right? Notice as I zoom in, the tangent line and the curve are almost indistinguishable as long as you're close to the target point, which shows that the line is really a good approximation for the curve near that point. But how good is it? Let's take a look at part B, and can I somehow paste this over? Can I copy this here and just paste it over? Bam. All right. Part B says, is this approximation actually any good? Like if I add a tenth to this number, let's see, plus a tenth would give 3.9, negative 3.9. So let's see how good our approximation is by plugging in that particular x value of negative 3.9. So negative 3.9 is going into this formula. And if you do 4 take away 3.9, you get a tenth. So we'd want negative 4/5 of a tenth plus 5. And we could work it out by hand, a little tedious. Or we can just grab a calculator, which I'm doing now. And let me see what that comes out to. 5 minus 4/5 times 0.1 is like 4.92. Whereas the actual value, now I'm using the original function formula, not its linearization. When you use the actual formula for that particular x value, let's see what you get. Negative 3.9 squared plus 9. Let's take the square root of that. The actual value is 4.92036584. So notice that our approximation was good all the way to the hundredths place. Pretty darn close. Okay, can we compute a ratio here? This is 99.99% accurate. Pretty darn good. Okay, let me leave it at that. Purpose of this video is to teach you about linearization, which is just really about finding a tangent line to a curve, finding its equation, all right, using it to approximate a function, and then deciding how good it is. Hope this video helps you to do that. We'll see you next time.